Let's do a few more examples where we have to describe the sampling distribution of the mean. So we're up to example 7 from the chapter 8 worksheet. So remember, the last thing that we did in the last lesson was this question, example 6. So example 7 says the number of violent crimes committed in a day possesses a distribution with a mean of 2.2 crimes per day and a standard deviation of 6 crimes per day. A random sample of 100 days was observed, and the mean number of crimes for the sample was calculated. Describe the sampling distribution of the sample mean. So I'm pretty much asking you to do the same exact thing that we did in the previous example. I'm just wording it differently. So when I say describe the sampling distribution of the mean, I'm asking for the shape of X bar, the mean of X bar, and the standard deviation of X bar. So I'm asking for those three things. So let's write this down before we get to this example. So let's go to the whiteboard for a minute. So when I say describe the sampling distribution of the mean, X bar, I want three things. I want you to tell me the shape of X bar, the mean of X bar, and the standard deviation of X bar. So it's those three things that we're using to describe the sampling distribution of the mean X bar. So let's go back to the examples. So it says here, we have a population of crimes per day. Well, we're looking at days, right? So we're looking at and particularly we're measuring the number of violent crimes that are committed in a particular day. So on average, the mean number of crimes per day is 2.2. So we're being told that mu is equal to 2.2. And there's a standard deviation of 6 crimes per day. So sigma is equal to 6. Now, if we take a random sample of 100 days and we observe how many crimes were committed, for each one of those days, let's describe the sampling distribution of the sample mean. So for each one of those random samples of 100, we're going to calculate X bar, which is the mean number of crimes for that sample size. So 1, let's describe the shape of X bar. Now, you have to, just like we were doing before, right? The thing that makes it a little bit easier in this previous example that we did is that I gave you a picture of the shape of the population that we were sampling from. Here, I took away the picture. So we have to kind of read into it, right? So does it say anywhere in this example about the shape of the number of crimes per day? It just says it possesses a distribution that has a mean of 2.2, a standard deviation of 6. We're going to take a sample of 100. There's no mention of the shape of the distribution. So we're sampling from a distribution right now where it's unknown. I don't know the shape. It could be normal, it might not. So we can't assume that X bar is normal because we're not sampling from a normal distribution. So now we have to look at sample size. So is the sample size bigger than 30? Because if it is, then we could apply the central limit theorem. It is in this case, right? 100 is bigger than 30. So we can say that X bar is approximately normal, since n is bigger than 30. So we applied the central limit theorem. Now I also want you to tell me the mean of the sampling distribution of the mean, and that's equal to mu, which is 2.2 in this case. And then we have to calculate the standard error of the mean, which is sigma sub X bar, and that's sigma divided by the square root of n. So we're going to take 6 and we're going to divide it by the square root of n, which is 100. And that's going to be 0.6. So X bar is approximately normal and it has a mean of 2.2 with a standard error of 0.6. So let's look at the next example. Example 8. So now we're looking at people in a certain population and we're measuring their height. So the heights of people in a certain population are normally distributed with a mean of 67 inches and a standard deviation of 3.1 inches. Again, let's describe the sampling distribution of the mean now for samples of size 35. So we're looking at a distribution of people's heights, and we were told that height is normally distributed. So height is normally distributed with a mean of 67 inches and a standard deviation of 3.1 inches. So let's write this down. So the mean is 67 inches and the standard deviation is 3.1 inches. And we know we're sampling from a normal distribution. And we're going to take samples of size 35. So n is equal to 35. So again, let's describe the sampling distribution of the mean. So I want those three things. So tell me the shape of X bar. We'll describe its shape. We'll get the mean of all the X bars, and then we'll calculate the standard error of all the X bars. So the shape of X bar is going to be normal. Reason being is because we're sampling from a normal distribution. We don't even have to look at sample size, right? As long as you're sampling from a normal distribution, regardless of sample size, X bar is going to be normal. Mu sub X bar is equal to mu, which is 67, and sigma sub X bar is sigma divided by the square root of n. So we're going to take 3.1 and divide that by the square root of 35. So let's do that. 3.1 divided by the square root of 35. And let's go 4 places. So that's going to be about 0.5240 if we go 4 places. And let's do one more just to make sure we really have the hang of this, because it's really important that we understand how to describe the sampling distribution of the mean in order to do what's next, which is our application question. So now we're actually going to apply these concepts in the next lesson. So let's do one more. It says the heights of people in a certain population are skewed to the left with a mean of 65 inches and a standard deviation of 3.5 inches. For samples of size 15, describe the sampling distribution of the mean. So very similar to the one above, we're looking at a population of heights. So height is my variable, and we know that height in this case is skewed to the left with a mean of 65 inches and a standard deviation of 3.5 inches. So let's write that down. So the mean of the distribution is 65 inches and the standard deviation is 3.5 inches. And we know the distribution of height is skewed, particularly to the left. So we're going to take samples of size n equals 15, and let's describe the sampling distribution of the mean X bar. So we want the shape of X bar. We want the mean of all the X bars, and we want the standard error of the mean. So we are sampling from a non-normal distribution, right? We're sampling from a distribution of heights that's skewed. So we can't just assume that X bar is normal. We have to look at sample size. But are we able to apply the central limit theorem? We're not, right? Because n is not bigger than 30. So since we're not sampling from a normal distribution and we can't apply the central limit theorem, the shape of X bar is going to be unknown. We just say unknown. We don't say not normal. It could be, we just don't know. So now mu sub X bar is equal to mu, which is 65. And let's calculate the standard error. So we're going to take sigma divided by the square root of n, and we're going to get 3.5 divided by the square root of 15. You guys could plug that in your calculator with me. So 3.5 divided by the square root of 15. And to 4 places, we get 0.9037. So in the next lesson, we'll move on and we'll start looking at application questions. So how do we now take these concepts about the sampling distribution of the mean and apply them?